And so last time, if you remember, we were talking about the dense water formation, about the vertical convection, and we mentioned what is going on in the Adriatic, which is this thing here, and how we can see the vertical convection looking at the chlorophyll distribution at the surface, or looking at the phytoplankton concentration at the surface. And this thing here, in fact, this patch of the high or low chlorophyll concentration, or high or low phytoplankton concentration, can be seen also at the monthly means. For example, you can see here what is happening in February. In 1 year, this is 99 by chance, but you can look at any other year. What you can see here, this is the Southern Adriatic, where we were looking the evolution on a short time scale of this patch of the high phytoplankton concentration. And you can see that in February, this patch is dark blue. So that means in the February, there is not yet the vertical convection. Oh, there is a vertical convection, but there is no phytoplankton bloom. And the same thing happens here. In this is what this area is called Gulf of Lion. In Gulf of Lion, another area of the Mediterranean where the dense water formation and vertical convection takes place. So in both areas where the dense water formation takes place, is the low phytoplankton concentration in February. You have to remember that why we always study these dense water formation or the vertical convection, because these processes are driving mechanism of the entire conveyor belt, or in the ocean, or even in the Mediterranean, because here the dense water which is formed here, it goes down, it's spreading here, and it drives the entire deep circulation over the Eastern Mediterranean. The same thing is happening here, or similar, or equivalent. Here you have a dense water formation where the water goes from the surface to 2,000 meters and then spreads all over the Western Mediterranean, driving the circulation cell of the Western Mediterranean. So that's the important thing. Why do we study these dense water formation processes? When we go to April, in April the situation is completely different. It looks like a negative photography, and because you see that here where used to be the blue, dark blue patch, now is the yellowish, greenish patch, and here where used to be the bluish patch, dark bluish patch, here is the reddish or yellowish patch. So that means that in April there is typically the dense water formation and the phytoplankton bloom. So that's how it looks like also at the monthly scale. So the months, or at the month, if you do the average over the entire month, you would see the signs or the signals associated to the vertical convection from the chlorophyll data, from the phytoplankton density, phytoplankton concentration in the surface layer. Here is, for example, in July everything is smooth. There is no any specific patch around. Everything is very poor in phytoplankton because there is no vertical mixing, because the water column is vertically stable. If you remember, on the vertical distribution of temperature, surface layer is warmer than deeper layers. This is in summer. So that means that the surface layer, you have the lighter water on top of the heavier water. So this is the stable conditions. So stable conditions doesn't stimulate the vertical mixing. Therefore, there is no water exchange between the deeper layers and the surface layer. But not having this exchange, the phytoplankton consumes all the nutrients in the surface layer, and therefore after sometimes becomes getting lower and lower concentration, because there is nothing to eat, nothing to consume. And therefore in the summer season you can see that everything is dark blue color, which means the low concentration of chlorophyll over the entire Mediterranean. And the similar thing happens in other areas of the dense water formation. Now let's see. You remember this the figure which shows the global conveyor belt. Global conveyor belt which shows the dense water formation north in Labrador Sea, and this water then spreads in the bottom layer and then going and doing its turn all around the Earth with a time scale of the order of 1,000 years. In that specific figure, it's we are missing the contribution of the Mediterranean. The contribution of the Mediterranean is adding another dense water formation source, because on one hand you have the dense water formation in the Labrador Sea, which is the dense water force, the main dense water force for the main dense water source for the global conveyor belt. But nevertheless, the Mediterranean Sea is at the same time also the secondary dense water force, dense water source. And here is how the Mediterranean situation looks like. In the Mediterranean, we have seen that Mediterranean has a higher salinity than the Atlantic. And why so? Because evaporation is stronger than precipitation. So we have a loss of fresh water from the surface of the Mediterranean. So we have the increasing of salinity over the entire Mediterranean. And that means that the water exchange between the Mediterranean and the Atlantic is such that in the surface layer, the Atlantic water enters the Mediterranean because it's lighter. Why is lighter? It's lighter because it has a lower salinity than the Mediterranean. Then goes eastward and reaching the easternmost part of the Mediterranean, and its way toward the east, due to the evaporation stronger than precipitation, loses the fresh water, becomes saltier and saltier and denser due to the excess of salinity. And then it sinks vertically, and so we have this convective sinking. We have the sinking because the surface water becomes heavier and heavier. And finally, as a compensation of this inflowing water in the surface layer, inflowing water of the Atlantic origin, we have the outflow of the water of the Mediterranean water in deeper layers of the strait of the Mediterranean, which is Gibraltar Strait, and it outflows. And then when it outflows from the strait, this is the strait and sill, it sinks down right after the sill and reaches the bottom, the depth equilibrium, and then spreads along the Atlantic. That's the Mediterranean type of circulation. So here is Atlantic, here is the Mediterranean, and evaporation larger than precipitation. However, there are some other type of Mediterranean seas or semi-enclosed seas where river and rain input is larger than the evaporation. In that case, the semi-enclosed sea releases the fresh water toward the adjacent ocean, and there is an inflow of dense water from the adjacent ocean into the semi-enclosed seas, where the rain and river input is larger than the evaporation. And this kind of semi-enclosed seas or Mediterranean seas obviously exist all as well. This is one of these, is the Black Sea in the Mediterranean. But we will be talking about this because this is the scheme of the Mediterranean water exchange between the Atlantic, and we just mention a few words on the Mediterranean as being the secondary dense water source for the Atlantic. And this is how it looks like in real life. The Mediterranean is here, the Atlantic is here, and the red arrow shows the inflow of the surface water, of the fresh water, fresher or so lower salinity and lower density water from the Atlantic into the Mediterranean. The Mediterranean water, on the other hand, exits in the deeper layer and then sinks down. You can see it sinks down after reaching the equilibrium depth. And you can see that the Mediterranean has here at the limit of the outlet of the inlet, of the Gibraltar. You can see that the Mediterranean has the salinity of 38.4 kilogram per meter cubic, while the Atlantic water has a 36 or 36.5 kilogram per meter cubic salinity, and this is the two units salinity differences between the Atlantic and Mediterranean water. And this is how it looks like in the vertical cross section from the Atlantic into the Mediterranean. What is people were able to calculate the inflow of this water of the Atlantic water into the Mediterranean by doing simply the current measurements here and not certain number of points and doing the numerical integration. And they obtained that this is from the Atlantic we have a 1.1 million meter cubic per second of the inflow. Then we have outflow from the Atlantic is 1.041 plus and you have to add up this here evaporation, and here is river runoff and precipitation. So you end up exactly with the same number. The total inflow of the Atlantic water is 1.15 million meter cubic per second, and outflow is 1.15 million meter cubic per second. So it's a huge, can you imagine this? It's a huge amount of water. And if you, for example, compare this with the rivers, with the outflow of rivers, which are typically on the largest river in the world is like 100,000 meter cubic per second. We are talking here about 1 million meter cubic per second. So that's almost an order of magnitude larger water flow than the water discharge than it is from the rivers. This is, now you can see how important is the water exchange or water flow within the ocean with respect to the contribution to the boundaries of the other boundaries like rivers and so forth. That's how it looks like if we move a little bit farther, and we don't look into details, but what we can see is that this water of the density of 38 kilogram per meter cubic exits the Mediterranean and then spreads at the depth of around 1,000 meters. So that's it. That's its equilibrium level, where the density of the water which originates from the Atlantic has the same density as the surrounding adjacent Atlantic water. So it spreads around 1,000 meters depth, and it spreads mainly or partly westward and partly toward north. Here it is. You look like here it is. If you look from top down figure, you can see traces of this higher density, higher salinity water originating from the Mediterranean. This is Gibraltar Strait. This is Spain. This is Africa. And obviously, this water doesn't have salinity of 38 kilogram per meter cubic anymore. It does have a lower salinity, but still higher salinity than the adjacent Atlantic water at that specific level. And you can see that this water reaches almost Gulf of Mexico. And so this is that's hi Alejandra. And so that's how it looks like. It looks like a signal. This is a signal which is which comes from the Mediterranean as a secondary source of the dense water for the global conveyor belt. This has a higher salinity, although it has the more or less the same temperature, but having a higher salinity has a relatively high density. And this pumps. This is another pumping source for the dense water for the global conveyor belt. Okay, that's it. This is we are not finished. No, don't worry. So now, so that's so far we have talked about the general introduction into the oceanography. We described the geometrical features. We described the parameter of state of the ocean and their distribution. We described in a very simple schematic way the global conveyor belt. Later on, we will be talking how, in fact, the climatic changes can influence the global conveyor belt, because since the main engine of the global conveyor belt is the northern Atlantic or polar areas, and partly also the polar southern pole area. Any climate change, what is happening and has a consequences on the northern or southern pole, certainly will have the impact on the global conveyor belt, on its efficiency, on its velocity, and so forth. And so, because the length for the formation, the vertical convection, would depend on the climate, a local climate in these two specific areas. Therefore, we will see later on how this climate change can impact and can influence the global conveyor belt. Now we can go on and let me see. Okay, where I am. I'm here. Can you see this? Can you see it?
Yes.
Okay. Okay. But it's small, right? It's not big enough. Can you see it?
Yeah, it's big enough.
Okay. So now, however, now we will be going into the dynamics of the circulation. The dynamics of the circulation means that we will be going to see the forces which are determining the flow. The forces which are determining the flow are in the equations, makes part of the equations of motion, where we have the horizontal and vertical component of the equations of motion. So we have the acceleration. We have the acceleration in all these equations. We have the advection of momentum. We have the Coriolis force, which we will be talking about in a minute. As the forces on the other side of the equation, we have forces which are pressure gradient force and viscous forces. So we have these horizontal components, which are x, west and west-east, and we have the y component is south-north, and then we have the vertical component where again we have acceleration, advection, pressure gradient force, effective gravity, and Coriolis. In the vertical, we neglect the acceleration and advection, and we neglected very small Coriolis force. We can neglect also advection because we are talking about a very weak vertical motions. These vertical motions, very weak vertical motions, are present everywhere except in the dense water formation areas, in the vertical convection areas. And these are the very limited space-time limited processes. That means that in general we can neglect the advection, so we have a pressure gradient force and effective gravity in the equations of motion. Let's I can put this now. Let me do this one another thing. I will first try to talk to you about the Coriolis force, and then we will go let me try just 2 minutes to find this. Okay, it is. Here it is. Okay, here we are. So we will be now just concentrating ourselves on the definition of rotation, centrifugal Coriolis force, and inertial motions, because this is one of the important terms in the equation of motion. Then we will go back to the complete equations of motion and find out the specific solutions, the solutions which are obtained by introducing simple approximations, and then which gives us the simple solutions, and we will be looking at where these kind of solutions and how efficient these solutions are in approximation of the motion in the ocean. Okay, so here we are sitting on the rotating Earth, which is to a certain extent an interesting evolution of the equations of motions, because it adds additional term, because we are really staying at the rotating reference frame. The quantity which tells us how fast we are the system is rotating is the angular speed or the angular velocity, which is the angle divided in a second. So these are radians in a seconds, and for Earth we have the whole the entire solution, the entire resolution is revolution is 1 day. So we have that the Earth, we have this is the quantity which gives us the rotation of the Earth, which is 0.7 times 10 to the minus 4 second to the minus 1.
Professor?
Yes?
I think you're not sharing your slides.
No? Really?
What we see is the
Oh,
lecture.
sorry. I will do it. I will... good. Great. You gave no condivisione. This thing? You don't see it?
Oh, we see it now, Professor.
It says rotating coordinates.
Yes.
Okay. Grazie. Thank you.
Thank you.
Okay. So let me see now. Here it is. Okay. Now everything okay? You can see it.
Yes, Professor.
Good. Okay. So we, as I told you, the Earth is rotating, and this is the angular speed or angular velocity. And this angular velocity on the Earth is 0.7 times 10 to the minus 4 seconds to the minus 1, which is the angular velocity what you obtain by dividing 2 pi by 1 day in seconds. We have just to tell you how did we do these experiments, the laboratory experiments. If you want to simulate the rotating system as it is here, like 2 years ago, 3 years ago, we have had an experiment in a rotating frame, in a rotating platform. So in Grenoble, in France, there is a large, huge rotating platform which is 14-meter diameter and is that deep, like 1 meter. You can fill with the water or 1 meter deep water. And this obviously, if you want to simulate the rotating coordinates of the rotating frame, you have to make you have to rotate your system, this system, which is this platform of 14-meter diameter, and but you cannot obviously make it rotate with in 1 day, which is such a slow rotation. You have to scale your rotation. You have to scale your rotation by comparing the total dimensions of the Earth ocean with your dimensions what you have in your laboratory. In your laboratory, that means you have 14 meters, and rotating Earth has the diameter of about 6,000 kilometers. So you have to redimensionalize, to limit, to make similarity, geometrical similarity between your laboratory and the Earth. So what we did is that instead of having these 0.7 times 10 to the minus 4 seconds to the minus 1, or 86,400 seconds of a rotating period, we used to have the 100 seconds rotating period in order to get this similarity, because we are talking about a smaller scale, smaller geometrical scale. Everything is smaller depth, and everything is smaller. Therefore, we have to reduce also the angular speed, or to increase the angular speed in order to get the similarity between these two. So this is one interesting experience what we had trying to simulate or make laboratory experiments addressing the specific features in the ocean. Anyhow, so we can show that sorry, that omega, which is v over r, where v is the measured velocity and r is the radius to the axis of rotation. We have the speed. The speed, tangential speed is omega times r. So it's proportional to the angular speed and the radius of the Earth. The radius of the Earth, as I said you before, is about 6,000 kilometers, and omega is 0.7 times 10 to the minus 4. So that's the fact that we are trying to resolve our equations in a rotating coordinates. And what do we have to do there for this? So first of all, we have to define the vector which defines this rotation, and the vector that expresses direction of rotation is, and how fast is it rotating, because every vector contains on the magnitude and in the direction. In the specific case of the rotation, the vector pointing in the direction of thumb, using the right-hand side rule, curling fingers in direction of rotation, this way, this gives you the direction of the rotating vector, and the magnitude of this rotating vector is this angular speed. Then let's see what are the forces which are acting on the ball, on the body which stays at the surface of the Earth. We have two forces which are centripetal forces, is the actual force that keeps the ball tethered. That it is the string, but it can be gravitational force. So it's a kind of a force which keeps on one hand keeps the ball at the surface of this rotating body, and then we have a centrifugal force, which is a pseudo force or apparent force that one feels due to the lack of awareness that the coordinate system is rotating or curving. And so we have this centrifugal force, which is omega squared r squared r, and this is obviously the units are meter per seconds to the square, and this is the outward force. So these two forces presumably should be in equilibrium, otherwise or the ball will fly out, or it will be brought toward the center of this body. So this is the what is the effect of the centrifugal forces on ocean and Earth? Centrifugal force acts on the ocean and Earth, and it is pointed outward from the rotation axis. So that means at the equator it is pointed this way here. At the here in mid-latitude is pointed here. Okay, perpendicular to the rotating axis, and this is rotating axis. You know that rotating axis is not really the vertical, but it's this way. Anyhow, if this is the rotating axis, the centrifugal force here is this way, and here is this one, and so forth. Therefore, the maximum of the centrifugal force is at the equator, because it's proportional. It is proportional to the radius, of or the distance of the body from the rotation axis. So it is the maximum at the Earth, the maximum at the equator, and minimum at poles where the radius is 0. So At the equator, we have a 6,000 kilometers radius. So omega squared r is this thing here, 0.032 meter per second squared. Compared with the gravity, which is the centripetal force, which is 9.8 meter per second squared, we can see that practically the centrifugal force can be neglected with compared with gravity. Anyhow, the centrifugal force should cause the equator to be deflected by about 21 kilometers compared with poles, about 0.3%. So the Earth is not really a ball, but it's the ellipsoid. But this difference is between polar, between these two is like only 20 kilometers. So the radius at the equator is 6,378 and so forth, while polar is 6,356. And the mean radius of the Earth is this thing here. This is from Wikipedia entry on the Earth. So the ocean is not really 20 kilometers deeper at the equator. It's rather the Earth itself is deformed, because the ocean, as you know, the ocean is maximum 11 kilometers deep. Therefore, this deformation due to the differential centrifugal force between the equator and polar areas is associated to the deformation of the Earth is associated with this varying centrifugal force. But since we are talking about the centrifugal force, which is with respect to gravity is 2 or even more orders of magnitude smaller, we simply bury the centrifugal force term in the gravity term, and so we call this effective gravity, and ignore from now on, we ignore the centrifugal force. Except for the calculations that require a precise gravity term, we should use we should use also the centrifugal force and its dependence on latitude and its latitudinal dependence. And this, in that case, we have to use the precise calculations on the centrifugal force. So in other words, the Earth is ellipsoid, is the elliptic form because of the changing of the centrifugal force with latitude. Now we come to another important force, which is acting at the Earth due to the fact that we are in a rotating system, which is the Coriolis effect. Coriolis effect is the apparent deflection of the inertially moving body just due to the rotation of you as observer. What that means, if we were in the absolute system, which is outside of the rotating Earth, and if you see the particle which is moving by inertial motion, so moving just without any forces acting during its movement, from the absolute coordinate system, you will see the particle moving in a straight line. Okay, since you are looking from the absolute coordinate system. And since we are on the rotating Earth, in the rotating system, we are really seeing something which is called, we see the deflection of that inertially moving body, just due to the fact that we are rotating with the rotating system. We as observer, we see that the particle which has been pushed in a certain direction and moves inertially is deflected due to the fact that we are observing the particle on in the rotating system. So that's why so the Coriolis effect, in fact, deflects bodies, water parcel, air parcel, to the right. To the right in the northern hemisphere, and to the left in the southern hemisphere. And this is what we see really when we look at the particles. So therefore, in order to describe the movement of the particles, the movement, the current field on a rotating system, we have to introduce another term, which is the Coriolis term. Coriolis term means that that without Coriolis term we cannot describe completely the movement of the parcels on the rotating Earth. So introducing the Coriolis effect or Coriolis term, we describe completely the movement of a particle in a rotating system. So let's go on. And here is how it schematically looks like. This is the intended path. Intended path means that the particle, without having any forces acting on it, it will move. It will get push into this direction. It will move this way. Looked from outside, from the absolute coordinate system. However, since we are here at the Earth, we will see the particle moving this way. So it will be deflected to the right, looking downward in the direction of the movement of the particle. This is so-called Coriolis deflection. And here is how it looks like. So from the north, if you push the particle, give a push to the particle from the North Pole southward, it will be deflected to the right, and in the southern hemisphere, it will be deflected to the left. Therefore, as I told you before, we have to introduce the additional term into the XY momentum equations. At latitude phi, horizontal motion is much greater than vertical. So this is in the vertical we can neglect the vertical component of the Coriolis force. And so this in momentum equation we have these two terms. In the x component, the momentum equation is this thing, and in y is this thing here. Here, this one, you have 2 omega sinus phi is the Coriolis parameter, which depends on the latitude, projection of total Earth rotation on the local vertical. So this Coriolis parameter, as you can see, is a function of the latitude. Therefore, so this is these two terms what we introduce into the momentum equation. So therefore, going back to what I started to talk to you is these three equations, equations of motion, 3 component of equations of motion. We have introduced the Coriolis term, where we neglected this very small Coriolis term. We have effective gravity, which includes the centrifugal force. We have viscous and pressure gradient forces, which are external, which are due to, one is due to pressure gradient. We will be talking a lot about the pressure gradient later on. Viscous terms are due to the viscosity, water viscosity, or to the different velocity between different layers of the water, or due to these viscous terms are also due between the atmosphere and the ocean due to the different velocity of the air and the water. We have also viscous term at the bottom due to the fact that there is a relative motion of the water with respect to the bottom, which does move. So these are the equations of motion in three components. And here how they are expressed, how they are developed in mathematical formalism. You have the local acceleration. You have these advective term. Advective terms means that the advection of momentum with horizontal movement. You have the Coriolis force, the pressure gradient force, and here are the frictional terms. And the same equivalent thing is in the y, and then there is this this vertical component. Now let's see some simple equations, some simple solutions of the equations of motion, which are in fact present in the world ocean, and so that's why they are interesting. They are interesting because the equations of motion, although they look rather complicated here, they can have some simple solutions which describes pretty well whatever is happening in the ocean with a certain approximation, obviously not 100%, but it represents a rather good approximation of the flow in the ocean. One of these solutions, or one of these current field which we have observed in the ocean is this what we call inertial currents, where we can see the Coriolis force in action. What happened? The people who were using the surface drifters. Drifters are simply the passive instruments, the passive construction, the passive instruments which you throw into the sea, and then they move by the currents. And people were looking at the movement of these. This is the trajectory. For example, this one here is trajectory of one of these drifters. What you can see, this wiggled thing, and which goes this way, and it progresses from here to there, but doing these wiggles in this direction. This was in the Gulf of Alaska during and after the storm. And what you can see is that the corkscrew drifter movement in a clockwise direction. In a clockwise direction, they move and they progress at the same time. What is happening is that they do this clockwise movement at the northern hemisphere. Again, you have to take into consideration the sign of the Coriolis force. In the northern hemisphere, it is opposite sign with respect to the southern hemisphere. So these inertial motions are clockwise in the northern hemisphere, while in the southern hemisphere is in anti-clockwise due to the changes of the sign of the Coriolis force. And so that's one thing. The other thing is that the period of these oscillations, the period of these rotations, clockwise rotations, which are all these wiggles are from different drifters. So the people, they put the number of drifters and they simply analyze their motions, and this is the result. All of these drifters show these corkscrews it shows these motions, this rotating motion, but but since there is a average current superimposed on it, it's not the closed circle, but it's open because the mean current takes these drifters in one direction. So that's. But how about the period? The period of these oscillations is what we call the inertial period. Inertial period is on the order of 15, 17 hours. Is certainly less than 24 hours. And how do we obtain the inertial current solution? Inertial current solutions is obtained as a balance of the Coriolis and acceleration term. So push the water and it turns to the right in circles. So what you can see here is that that in the northern hemisphere you have this kind of rotation. Obviously, if you have the average current, you don't have only the inertial currents. In addition, you can have also the mean motion. The mean motion means that the drifters which are rotating in 2 pi over f, where f is the Coriolis frequency, Coriolis. So we have like in this mid latitude, you have this period of the inertial period is about 17 hours. So in 17 hours, the particle makes a full circle. But since you have the superposition of the average current, this thing is not circle, but it's open, and it goes, for example, this way. So let's see really how the equations looks like. So if these are the approximate equations, you have to take into consideration that we have eliminated all these terms, all other terms apart from the acceleration and the Coriolis force. We eliminate, we assume the linear equation, linearized equation. So we eliminate the advection term. We eliminate the horizontal pressure gradient force because we are talking about very fast changes. We eliminate the frictional force because these kind of currents appear when the wind has blown over the air and then suddenly stopped. So it gives a push, and there is no any more force acting on the water parcel. And this is why it calls inertial currents, because it has the parcels are moving by inertia. So we have acceleration, we have the Coriolis force, and an XY direction. In the vertical, we don't have anything because we neglected the third component of the velocity. And these equations we should solve in order to obtain the inertial currents. So solving these simple equations, we can combine the two and obtain the very simple solutions for the inertial currents. We obtain the period and of this solution, and the period is, as I told you before, the period is 2 pi over f, where f is the Coriolis parameter. Okay, so this is one simple solution of these. Oh, here you are. Right. Okay, let me do again. Let's go back, and I will now give you a pass to another. Let's pass to another. No. Just a minute. Okay, now we'll go to oh, here it is. Okay. Do you see now it? Do you see now my scheme?
No, Professor.
No? Why? Okay, I'll do it. Okay. You don't see this?
We
Okay.
see the folder, yeah.
Ah, you see the folder. Okay, let me see. You don't see anything now? Well, still the folder? Okay. Let's see. Sorry. Conveyor lo schermo. Can you see it now? Do you see now?
Yes.
Oh, okay. It says dynamics 3 geostrophy, right? Okay. So now, since you see this, I don't have any secrets with you. We can start with what we call geostrophy. This is another. This is another simple solution of the equations of motions, which can be seen in the ocean, which can be seen in the ocean. So so we will be talking about the geostrophic balance, and so this is the force balance with rotation. As I told you before, we have here the complete equations with different terms. What we have also seen also with using the mathematical formalism, and so as I told you before, for inertial motions we have acceleration and Coriolis force. We kept only these two terms. Here also the same thing in a y direction. And now, if we are talking about the geostrophic flow, in that case, we should do the other approximation. The other approximation means that we will be neglecting the acceleration. We will be neglecting the advection term. So again, we will be keeping the non-linearity of our system. We'll be keeping the Coriolis force, pressure gradient force, and neglecting the viscous term. So our motion is steady, doesn't contain any time dependence in it. Our motion is non-viscous, and our motion is linear. In the vertical, we have just the pressure gradient and gravity. So we have the vertical pressure gradient and effective gravity. So this is another simple linearized solution of the equations of motion, which you will see later are rather well and rather good approximation of the world ocean circulation, of the large scale world ocean circulation. We will be analyzing in which conditions these approximations are valid, and what range of time and space scale are adapted, are good for this kind of solution. So this is this is just one example, but we will be coming this later. And also this thing here, and let's do this thing. What that means in a schematic way? What that means starting from the equations? What that means for our flow? For our flow, we have that the pressure gradient force balances the Coriolis force. Okay. So these two forces are in balance. This is the thing, right? Pressure gradient force balances the Coriolis force. These two are in balance according to the equations of motion, because we neglecting all the other terms. So these two, pressure gradient force and Coriolis force, are in balance. But what that means in terms of the flow? In terms of the flow, in order to get the Coriolis force exactly balancing the pressure gradient force, the flow should be in this way. So the flow should be in such way that leaves the low pressure on its left or high pressure on its right. That's the unique solution of these equations. The pressure gradient force being in a Coriolis in an equilibrium Coriolis force defines uniquely the geostrophic velocity, which is parallel to the lines of equal pressure, and leaving the pressure on its left, because we have defined the pressure gradient force as a vector, whose magnitude is the horizontal pressure gradient, and the direction is from high pressure to the low pressure. This is the definition of the pressure gradient force. In that case, the velocity should be moving from parallel to ISO from the lines of equal pressure, leaving low pressure to its left. Not only that, but not only the direction of the velocity, geostrophic velocity is determined, but also the geostrophic velocity magnitude, geostrophic speed is determined, because the speed should be such that the Coriolis parameter multiplied by v, by the component, by the speed of the geostrophic flow, should balance the pressure gradient. Okay. So this is the velocity of the geostrophic, but in the northern hemisphere. You have to always to remember that in the southern hemisphere, the Coriolis force is to the left of the pressure gradient force, and therefore the picture is I think it's here. No, it's not here. Okay, anyhow, in the southern hemisphere, you will have the pressure gradient force this way and the Coriolis force that way, and in that case, you will have the Coriolis, the geostrophic flow in this way. Therefore, if you want to really to obtain the velocity field, the geostrophic velocity field, it would be enough that we reconstruct the pressure gradient, the pressure field. So from the pressure field, we define, or we obtain, we uniquely define the velocity field, and so that's a very useful property of the geostrophic flow, because by measuring the pressure, for example, in the atmosphere, you can measure the pressure wherever you want. In a much simpler measure the pressure than the wind. And so then you obtain the pressure field, and then from that you obtain the wind field. And the same thing is in the ocean. Or let's see the other view onto the ocean. In the northern hemisphere example again, we have the pressure gradient force, which is directed from the high pressure to low pressure. Coriolis force from is to the right hand side of the velocity, or the velocity is such that the Coriolis force is to the right hand side. And so this is how it looks like if you look from up down to the ocean, onto the ocean. If we have the cross section, the vertical cross section across our ocean, and this is, for example, the sea surface of the ocean. This thing here, this is the sea surface. What is happening here? Here, the pressure is higher than here and then the air, because here the sea level is higher than on both sides. Okay, in that case, the pressure gradient force on this side of the hill, this is like a small hill, the pressure gradient force is from the hill toward the other side. And in that case, the geostrophic flow should be into the paper, into the slide, and because in order to get the Coriolis force in the opposite direction, let's say, to pressure gradient force. On the other side of this hill, you have the pressure gradient force is in the opposite direction with respect to the other side of the hill, and the Coriolis force is again in the opposite direction. And so the flow is out of the paper on the right hand side on this hill. So that means that if you have like a hill on the top of the ocean, then the flow will be, if you have the flow will be such that the hill will be left on the right of the particle which is moving around this hill. So if the particle is moving around the hill, it will move only in a clockwise direction around the hill, and vice versa. If you have the kind of a dip in the surface, deep on the surface on the ocean, the particle will be moving in the opposite direction. It will be moving anti-clockwise. So this already gives you the idea how we can reconstruct the flow field, not only along the straight constant pressure lines, but also along the different structures along the closed pressure lines in the world ocean or in the atmosphere as well. So this can be simply also understood in this way. Think of ball rolling down the hill from high to low pressure, and it will be turning right due to the Coriolis force in the northern hemisphere. So this is why we do have this current into the paper on the left hand side of the hill, or from the paper toward us on the right hand side of the paper. So these are the approximate equations. These are approximated equations of the geostrophic balance, where we, as I told you, we kept the Coriolis force and pressure gradient force in both x and y direction, and we have hydrostatic balance in the vertical, where there is the balance between the vertical density gradient and the effective gravity pressure gradient, vertical pressure gradient force. So we can start from the atmosphere, because in the atmosphere the geostrophic the geostrophic wind has been introduced very early, and as soon as the analysis of weather maps or synoptic maps has started, the concept of geostrophic wind has been introduced, because this is as it was shown later, this is the very good approximation of the real wind. And from the very beginning of the evolution of the observation in the meteorology, the people started to reinforce the pressure measurements on the Earth, at least on the land. At the ocean, it was rather difficult because there was no way to have fixed stations at the open ocean. For some period, like around 50 years, there was a whole fleet of meteorological ships in the northern Atlantic, which were more or less staying there and measuring not only the atmospheric pressure, but all the meteorological parameters. So when we reconstruct the pressure field from the pressure measurements at the land, at the level of at the sea level, we obtain series of high and low pressure, and knowing this characteristic of the geostrophic flow, the geostrophic wind, we can immediately know what is the direction, and also, up to a certain extent, what is the magnitude of that wind. The closer are isobars, the lines of equal pressure, the higher is the wind speed, because here is you can see it from here. The higher is the pressure gradient force, the higher is for the same latitude, the higher is the wind speed. Okay, so the closer are isobars, the higher is the wind speed, and vice versa. Therefore, we are able also not only to estimate the direction of the wind, but also the magnitude or the strength of the wind. If you see for example, the measurements of the pressure field near the tropical cyclones, you will see that they are very, very close to each other. They are very close to each other because there the wind is very strong, very high. And indeed, if you look at these, analysis, you can see, for example, here is a low. That means a low pressure. So the pressure gradient force is from high to low. So the pressure gradient force goes this way, from the border to the center of the cyclone, and therefore the only possibility for the wind to go around this low would be in this direction, the anti-clockwise direction. So in order to guarantee that Coriolis force is in the opposite direction of the pressure gradient force. Therefore, if you see the low in the pressure field, you immediately know that there is cyclonic or anti-clockwise flow. You remember, cyclonic means anti-clockwise, and anti-cyclonic means clockwise. A little bit confusing, but you will be adapted to this sooner or later. Then there is a high pressure. In the case of high pressure, we have a clockwise flow, And here you can see that the pressure gradient is relatively weak with respect to this one. So the flow here around this high is much weaker than, for example, here. So these are this is the weather map, the weather distribution, the atmospheric pressure distribution for one specific day, from where a long time ago the oceanographer, the meteorologists, they simply would make diagnostic maps of the wind field based simply on the geostrophic approximation. Here is the let's see the geostrophic flow in the ocean. The geostrophic flow in the ocean is more or less obviously shows the same characteristics. Shows again that there is this geostrophic balance and so forth. That the flow around low and high, around high is clockwise around low is anti-clockwise, and high is clockwise. So what in that case what we should do? We should simply calculate, or we should simply have in order to get the information on the surface geostrophic circulation, we should simply measure the sea surface. And if you remember, I was talking to you about 2 lectures ago. I was talking to you that in 1992 there was a big change in the progress in oceanography when sea level measurements from satellites started with a series of satellites, and then there has been still going on these measurements from 1992 on. This we have already almost 30 years. These measurements then gives us every 10 days the whole pattern of the sea surface of the world ocean. What that means, not only the horizontal distribution of the sea level, but it means also the knowing what is the surface geostrophic flow. Exactly the same thing as in the atmosphere. As you remember from this graph what I showed you before, if you have a high, then you will have the clockwise flow, and if you have low, you will have anti-clockwise flow. So that means that our sea level measurements in the ocean gives us the average or the surface flow in the world ocean for the specific period. And this, as I told you before, the entire world ocean has been covered in 10 days. So if you do the 10-day horizontal distribution of the sea surface, we obtain at the same time speed and direction of the geostrophic flow. Okay, so this is one of these examples which gives us the distribution of the geostrophic flow in the world ocean in the Pacific Ocean. And when we have as we have seen also from sea surface maps, we have a low sea level in mid-latitude, then we have a high sea level in subtropics, another high in another subtropics, and we have a low in mid-latitude again. If we remember geostrophic flow characteristics, that means that around this high and around this high, we will have the clockwise flow. And so what that means that since the Coriolis force changes the sign passing through the equator, the two highs gives the same direction of the flow along the equator, simply because of the changes of the Coriolis parameter, of the sign of the Coriolis parameter. And then we have a low in the mid latitudes and low in the mid latitudes, and then we have here counterclockwise flow in that area here. So from by looking at sea level, we obtain the general circulation of the world ocean, and we will see later to what extent this picture, what is shown here, for the specific snapshot, what this is similar, to what extent is this similar to something what we call the world ocean circulation or world ocean conveyor belt. And so that's something which would confirm to what extent the geostrophic flow is representative of the average flow in the world ocean. So, okay, let's see the altimetric surface height. Altimetric surface height is exactly what I told you before, is the height of the sea level with respect to geoid, as you remember when I introduced to you this thing. And you can see that the sea surface height is that the sea surface is high in mid latitude northward, in mid latitude in a sub-equatorial region here, and in northern and southern hemisphere. The same thing you can see in a Pacific, in an Indian Ocean, and a similar thing you may see in the Atlantic. Obviously, the height of the sea level above geoid is not the same in different oceans. So we have, and then we have a bluish thing. Bluish thing is the lower sea level with respect to this one here. But what that means, high and low sea level. High and low sea level means high and low pressure in the ocean, because the higher is the water above you, the higher is the pressure, the higher is the weight of the water, because the pressure in the ocean is nothing else than the weight of the water column above the certain depth. So the higher is the sea level, the higher is the pressure in the ocean. Therefore, these yellowish, orange type of orange part of the ocean means the high pressure areas. The low pressure areas are bluish, greenish areas, and or low sea level. And if we compare this with surface circulation, and this is what we obtained here. Let's look, in order to not to lose too much time, let's look into the Pacific, for example, where, as you can see, in the Pacific, the signal associated with the sea level is the strongest than any other else. And you can see that around these yellowish or orange area is the subtropical high sea level. But then you have also at the same time subtropical subtropical gyres, which are running around this high, leaving this high sea level on its right. Then we have a subpolar, or I call it also mid-latitude gyre, subpolar gyres which are in a counterclockwise direction, leaving a high sea level again on its right. And then there is here something which extends all over the oceans, which is a very strong current running around the Antarctica. And as you can see, this why I say a very strong current. It's very strong current because if you look at the isolines or lines of equal height, you can see that they are very close to each other, which means that there's an extremely strong current running around the Antarctica. And so here we have the current flowing this way, and here there is the current around the Antarctica flowing that way. So this is Antarctic current, which is very strong, which is also partly due to the wind, because the wind pushes the water in the Antarctic area and creating the horizontal pressure gradient, horizontal gradient of sea level, and creating this geostrophic flow around the Antarctica. See, this is these are the Antarctic circumpolar current, which flows all around the pole. And so you can see how similar is the distribution of the sea level with the circulation, with the circulation which is obtained in an independent way. This has been obtained in another way. This has not been obtained from this thing, but it's obtained with another independent measurements, and you can see how they are similar to each other. Okay, so again, this tells us that how representative of how good is the geostrophic approximation in the world ocean, not only in the world ocean but in the atmosphere as well. I always have to remind you, you should remember all the time that the whole prediction in the meteorology, whole meteorological analysis has been based on the simple geostrophic assumption, in which once upon a time, the predictions has been done from the analysis of the pressure field, and then what meteorologists they simply analyzed this pressure field and reconstruct the geostrophic flow and obtain the areas where there's a high clockwise, high anti-clockwise flow, and so forth. And then they predicted the movement of these closed structures westward or northward in function of the empirical knowledge at that time. Now everything is based on numerical modeling, so it's a different story. Now I will stop here, and we will go on Monday at the same time. Since I don't have any questions from you, I presume that that everything is clear, or nothing is clear, or everything is too simple, or everything is too complicated. I have 4 possibilities. I will, as an optimist, I will pick up the best one, the most positive one. Anyhow, I wish you all the best. Have a good weekend, and see you on Monday. Okay.
Have a good weekend.
Bye.
Thank you.
Thank you.
Bye bye.
Thank you.
Bye.
Bye.
Have a nice weekend.